Hello everyone, welcome to my channel. So today we're gonna go over some paper 3 practice because it's gonna be coming up real soon. So we're just gonna go over like a couple past papers. This is from like 2025, I think. Yeah, May June 2025. Sorry. Okay, yeah. And then we're just gonna go over 3.1, 3.2, and 3.4. So essentially, um, this is how I personally practice myself. It's just that I take the previous papers and then I just look at each connection between each problem, and just understand how we get to each problem after each problem. So we're not going to do exactly like the data part. So for example, where is it? Right here. So they want us to graph a table, right? I'm going to show you how to set up the table, but I'm not actually going to like write the table and make up data values because that's not necessarily true. Not necessarily like I've done that before. Um, but I am going to show you kind of how to draw this graph here. And how to approach it, but I'm not going to graph like actual values that are plausible in this experiment. And I'll quickly go over this, but the actual numbers, there won't actually be a lot of numbers. It's just going to be a lot of theoretical stuff. I'm just assuming a lot of arithmetic proficiency currently. So yeah, without further ado, let's get into it. And also, yeah, I'm not doing all the labs, so like this one I'm gonna skip. I'm just gonna do the springs and the electrical stuff. All right, so for 3.1, in this experiment, you will investigate the oscillation of masses on springs. You have been provided with masses and springs as shown. All right, so we have this setup here. First thing you want to do is copy it, basically. Copy the entire setup by itself. And they actually, in terms of AICE Physics, they're actually really generous giving you the actual diagram. In terms of like AICE Chem, you have to set up everything um, by yourself. They only give you water instructions, which is kind of annoying in my opinion. A helpful tip for setting up the springs. So at least in my school, the lab, the 100-gram mass hanger plus a 100-gram mass, if you put it like halfway through the, what is it called, the ring stand, it'll actually rest on the table here, which is not what we want. So another way we can do is just hang it off the table. So assuming this is the table, right? We can just hang the mass off the table like this, so that when you actually have the thing, you'll actually have enough space. Because depending on the spring, the elasticity of the spring, right, you might have different things. And then we'll just draw a hanger here. It might be like this, right? And then when you pull it down, you have some extra space. So that's pretty good. So we want to ensure both masses are the same level. So if one of them hangs off the table, you want to make sure the other one is also hanging off the same table, at the same height, basically. Another helpful thing that you could do, I haven't tested this myself, but it was brought up by my teacher, is that you can actually put a ruler or a meter stick on the side here. I'm assuming this is a very long meter stick, right? And by doing this, you can actually measure the distance you're pulling down the spring, as well as measure each length, depending on the lab, right? Sometimes they ask you for this length. So, and then we want to watch the oscillations and the mass initially oscillate in place, then out of phase, then back in phase. The number of oscillations of mass S from release until the masses are back in phase for the first time is N. So we want to count the number of oscillations, and we should have no units then because we're just counting a finite value. Technically it has infinite sec figs because it's only measured. But yeah, so for this experiment, you do need to have some intuition of doing it. I guess you just release it and just count this one, the left one, the mass S. This is crucial. And remember that an oscillation is up and down. So when you go up and down, that's one oscillation, and you want to count as many as that. You can do this once, but to get the second mark, you need to do it at least twice. So like trial 1, you want to say like, oh, I got n0 is equal to 5. Actually, this is not a plausible number. 20, right? And then like trial 2 is going to be like 22, right? n0 is equal to 22. I count 22. And then when you actually do this, you want to make sure that you find the average. This is similar to like AICE Chem, I'm pretty sure. So yeah. So let's go into the next one. Add a mass of 30 grams to mass S. The atom mass is M. Record M, so we can say that it's going to be 0.030 kg. Technically, it can just be this because it's only one sig fig. Repeat A, the number of oscillations of mass S from release until the mass is this. Okay, yeah. So in this case, it's going to be only one mark, and I'm looking at the mark scheme right now. It says that the only thing that matters is that n is less than n0, but honestly, you should just try it twice. So like I do trial 1, I get n is equal to 15, trial 2, I get n is equal to 12, so then I think you just rounds, I guess. N is equal to 13. No, 14, right? 27, 13.5, 14. Just say it's 14. All right, so calculate n when this is this. I'm sure that we can all calculate this. It's a simpler arithmetic problem. Sorry. Yeah, you just take 21 minus 14. So go to 7. You just say 7. Yeah, and the only mark is that. All right, so vary m by changing the number of 10-gram masses added to S and determine n. Do not use m equals 0. Repeat until you have 5 sets of m and n. Record your results in a table, including values of n. Also include the values of n cubed to 3 sig figs. All right, so let's actually draw our table. Wait, I think I can do. Oh, can I? Oh, okay. The software's goated. In the actual lab, you should have. I'm not entirely too sure if you have anything here, but you can probably get a straight edge. Helpful tip: you could use your ID as one. If you don't have like a ruler or a protractor, something like that. So we're gonna draw this across. This across again. Let's add one more here. Another one here. Another one here. And honestly, this is probably enough, so I'm just gonna right here. Trial 1. Wow, my line was so wonky, they didn't even recognize it. So we want m, right? That's as s. So we can write grams here. And simple because we're adding to s, I mean you can add an extra data value. This isn't really necessary, I feel like. And determine n. So n is going to be your recorded value, right? So this has no unit. Oh god. And then we need big N, and they give us big N is here. So we're gonna write n, and then we have n cubed. Yep. So we have this, we have that, and I'm sure that's everything good. In the mark scheme, it says that each column heading must contain a quantity and a unit where appropriate. So like this, like that. There's no unit for these. So, yep. The presentation of quantity and unit must conform to accepted scientific convention, which is as shown here with the grams. So we want to do a trial 1, trial 2, trial 3, trial 4, trial 5, and trial 6. And then since it's 10 gram masses, we'll just do 10, 20, 30, 40, 50, and 60 grams. In the data table, you do not want to write this because technically you already wrote it up here. Depending on the experiment, you might be asked to do an additional trial repeated. I'm pretty sure I've been told that's for circuits, but you can also do like a trial 7 for 60 and just redo everything just to make sure that you indeed get a similar answer. But yep. And another thing to mention is pay attention to the question. They want 3 sig figs. So plot a graph on n cubed on the y-axis of m, draw a straight line of it, and determine the y-intercept. Okay, so let me zoom out here. So notice that depending on my quality, if you see big squares, which is just like 2 by 2 small squares, there's going to be 8 on this side, and I'm pretty sure it's 10 on the top, right? 2, 3, 4, 5. 1, 2, 3, 4, 5. I remain correct. I think it's 12. So it's 8 by 12, I'm pretty sure. And the thing about AICE is that they want you to use pretty much the entire thing. So on this side, we have M, which is obviously going to be grams. And then on this side, we're going to have n cubed, I'm pretty sure. Yes, m cubed. And then we want to draw the appropriate axes. So we want to draw the appropriate axes such that it takes up half and a half of at least the entire graph paper. More specifically, like the scales must be chosen so that the plotter points occur at least half the graph grid in both x and y directions. So I assume it's like if we have a point here and we have a point here, we want to make it so that these scales make sense. For example, if we got a point like this, right? If our original scale was like this, we want to quickly erase this in our current scale and make it so that the difference is more apparent. So in this case, this is four big squares, right? So it's half of the x-axis, and vertically it's 4 big squares, which is not quite half of the y-axis. So we can add like, depending on the data values, you might have like something like this, which is kind of a bad measurement because they're so far apart. Technically these aren't together actually, but if you have something like that, this works. This works because you have covered up most of the things, and you want to make sure your scale is on the right thing. Also, you don't want to make up random scales. Just use multiples of 5 and 10, and that's pretty good. In terms of plotting the points, they require you to have diameter of less than half of a square, half of a small square. And a way to fix that is just draw X's, because your pencil or pen should be small enough to be less than that. And if you draw, it's basically like if you have a pen, you just like dot it, like you just dot. But if you press too hard, your dot might be too big. So you might as well just like kind of freehand it, but just make sure that you intersect the right place. Pretty cool. And then the final mark is going to be equality. So in this particular case, the n cubed values have to be positive, and the trend of the points must be positive. So in this case, we can say that it is positive So the best line of fit would probably be something like, no, that's too strong. Probably something like this. Like here. Here, probably. And yeah, and it must be positives to draw a straight line that is within plus or 5 grams of the m-axis of all plotted points. Okay, I'm too unsure about what that specific mark is, but yeah, whatever. But a key thing for these types of graphing problems is that we can actually take out a point. So for instance, we can just say, oh, this point's an outlier. This is bad. I'm going to disregard this. Right? You want to clearly mark that as disregarded. And then now you have best line of fit, something like this. And wow, it's so much better. You can clearly tell that it goes through half of the points, right? Pretty much. It's way better. Yeah, and then when you're calculating gradient, the next part. So we plotted this, right? Okay, so now we're gonna draw the best line of fit. Just draw it. Just try your best. I don't think they're looking too far, but the general things you want to keep in mind is half and half on each side. So half of the points are on the top, above the line. So on this side, right? And the other half on this side. That means that my best fit is kind of problematic. So yeah, the software's not letting me, but essentially you just want to try your best. And it's also telling you that it can't be too thick. So you just want to do a quick stroke. You're good. So that's that. And then the gradient and the y-intercept, make sure you draw a big triangle between the 2 points you're trying to look at, the 2 squares, and then calculate your change in y over change in x. Divide this, and then you get a gradient. And then simply use the y equals mx plus b. Using your y0, x0, and your calculated gradient, and then you can solve for your y-intercept. This is all Algebra 1 knowledge, so I assume that you guys have some pretty strong skills in this. And E, it is suggested that the quantities of n and m are related by this equation where p and q are constants. Using the D3, determine the values of p and q, give appropriate units. Okay, so this is actually the same as this part. So we can just say like this is our gradient from last question. Plus m is grams, so it's going to be grams -1. Wait, I'm going to further explain this grams number 1. And then q is going to be our y-intercept from last problem. And it's going to have no units. So how do I know it's going to be no units? So we do some unit analysis. N has no units, so it's going to be no units squared, which is still no units, or no units cubed, my bad. So then we have p units times grams, right, plus something. When you're adding these two, you're going to retain the same amount of units. So these 2 units have to be equal to no units. So that means q has to have no units, and this also has to be no units. So that means that p is grams -1. So then this becomes simply p, which has no units. And then, yeah, that's essentially how you do unit analysis for this. This one, I'm gonna skip this one. Oh yeah, I remember this one. My teacher was telling me about how the paper didn't actually curl during the actual exam, and a lot of people's exams got screwed over. But it is what it is, right? All right, so we're gonna go to 3-2. So this is pretty cool. This is a circuit problem. The switch ammeter, 1.5 volts battery, and you have this thing, thingamabobber. So we want to follow these instructions. Um, when I was doing the lab, the thing that actually helped me the most is just like actually doing the diagram shown in here. Um, so for example, like I'll actually set up my battery on the left side of this table, and then I'll have a connecting wire, right? And then I'll connect it to, sorry, this is a resistor. Oops. Yeah, so I have my battery up here. I'm gonna draw the battery like in real life, right? And I'm gonna connect the clamp to my resistor, right? And I'm gonna clamp it here, and I'm gonna clamp it here, and then I'm actually going to have it open here, I think, right? And then we put it like that to the thing, and then we connect this to the area, and then you want to have your like little switch thing with the two things, and you want to put them on here. Forgot there's a switch here, so we have connecting to the switch, right? Excuse my terrible drawing, but yeah, this is generally how it is. And then when it's down, you want to put the two parts of the thing here. Yeah, you just want to make sure that you take the positive value, I'm pretty sure, because yes, I'm not entirely too sure what the direction is supposed to be, but I just assume everything is positive, and I assume that Cambridge actually wants it that way. The same thing as for volts. You can't really have a negative voltage, so you might as well just do the voltage positively. If you get a negative voltage, just switch the red and black wires here. It's pretty cool. So measure the distance between the tape and X. Measure and record X. Go ahead and do that. So for our meter sticks, for us, it's gonna be like something something dot first decimal place, and then like an estimated value, like 0 or 5, basically. This is our estimated, and this is in centimeters. So we're gonna remember that this is actually in 4 sig figs. And in terms of labs, you have to kind of understand what sig figs are. If you don't really understand sig figs and how you do calculations with them, I suggest that you do a small review. You can use Organic Chemistry Online Tutor, or whatever his name is, and watch his sig fig video. It's pretty straightforward. It takes like 10 minutes to 15 minutes tops to understand it all. But yeah, and then we obviously read the ammeter. Depending on the lab, for ammeter, for voltage or current, you might use different settings on this little device here. So you want to make sure that you set the correct unit, basically. The table problem. Pretty good rectangle, eh? So I'm gonna go ahead and draw another table here. What I found is that the AICE Physics and the AICE Chem Lab are pretty similar in the fact that the tables are really consistent. So you want the trials to be pretty much on the side, like the rows, and then you can have the measurements on the side here, like here, 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 here. And it's actually really useful because it's kind of hard to continuously add here because you might have some really long description. So yeah. During all this time, you can either use a ruler or meter stick. I'm not entirely too sure on the policy of using your ID, but honestly, they don't confiscate that, right? So you can just use that as a straight edge. It's actually pretty useful. When I was in geometry class, I used to use it all the time because I don't want to break out my straight edge. So we want values of x. X is going to be in centimeters in this case because our ruler's in centimeters. And then I, which is our current measured, which is going to be in amps. And then we want including values of square root of I. So it's going to be a to the 1/2, right? In the mark scheme, you can do milliamps depending on your ammeter. But yeah. Consistency, all values of x must be given to the nearest millimeter. So yeah, we've done that. Let me look for more. Okay. Okay, so this guy lied to me. Whatever. Anyway, you should always try and do at least one more trial just to make sure that your thing is correct. So for this one, you might have 5.0, 7.0, 9.0, 11.0, 13.0, 15.0. And then like, you want to repeat this like 15.0. Let me look at this. 4 to 18, sorry. My reading skills are not very good, as you can see. So you just want to do a 4.0, and then we can do this back to 18.0. And then you just want to figure it out. You can do it somewhat evenly in between. Honestly, it doesn't really matter too much. And then you measure it, put your stuff here, and then square root it, and etc. And then you just fill everything out, and it's pretty straightforward. And you're gonna have this empty space here. They don't care. Just cross it out or something, or just leave it there, because honestly, they're just looking at whatever you actually fill out here. So plot a graph of square root of I on the y-axis. Okay, so it's pretty straightforward. Yeah, it's the same thing, pretty much what we did last time. So essentially, we're gonna skip that. Okay, let me see if there's. Okay, I guess so. I guess, bro. Okay, yeah, so we're gonna skip this and we're gonna go on to 3-4. Mainly for 3-4, we're gonna go over question 2. So it's actually about dropping balls through a water in a tube. Okay, this is this is actually a pretty funny experiment. All right. Okay, so we have this Y2, a tape marker, a wooden strip, a tape marker, a narrow tube, tray bench. Okay. And basically, we're essentially we're taking the balls, according to diameter, fill the syringe with water, Y2 watch it fall down, use a magnet, drop one of the larger balls, etc. Percentage uncertainty. Okay, so this is a new question. So for percentage uncertainty, you want to, I think it's like K2 minus K1 absolute value over the average of K1 and K2. And you want to put this value over here. And how we get this, wait, actually this is the wrong part, sorry, tweaking. It says percentage uncertainty. So t in this case is the time, so it's going to be 0.00 seconds. So then our absolute uncertainty is going to be 0.005 seconds. And then we want to just take that over our average value of t, and then you should get a percentage. yeah, we have T1 and T2 here, assuming that you do 2 trials. Pretty much for this part, you always want to do 2 trials. This is like the same in AICE Chem. So yeah, 2 marks for 2 trials. Yeah. And we do the same thing here. T1, T2. This one's actually 3 marks. I'm actually genuinely curious why. 2C. Okay, so they give you a mark for T1 is less than T2, where this is the first T, and this is second T. Pretty cool. And then using your data, calculate the 2 values of K. So just 1 over T, plug in T, you have K, D squared minus D is this, and then just plug in these values. And you want to justify the number of sig figs, so for T, it should be 3 to 4 sig figs, depending on how long it actually takes, but I'm assuming it's just going to be 3. And then this measurement here, we can say it's like 3 sig figs. So then when we actually calculate everything, in the end, we should get 3 sig figs. If you want to include 1 more and it's become 4 sig figs, that's also fine. That's okay. I'm pretty sure they do accept that, as long as you justify it. That's the thing. And then suggested that the percentage uncertainty in the values of K is 10. Using this uncertainty, explain what your results. Okay, so in this area, you use the this formula here. So K1 minus K2 minus K1 divided by the average here. And then you should get a percent. And if say it's X, the percent is less than 0.1, supports, X greater than 0.1 does not support, and this is all they're asking for. Describe 4 sources of uncertainties or limitations of the procedures of this experiment. So this is probably some of the easiest marks, but depending on the experiment, pretty much out of these 8 marks, probably 4 marks are guaranteed based on memorization alone. So one of these is that one of the problems is that we only do 2 measurements, which is obviously a problem, because how do we know that these 2 measurements are not just like flukes that are somewhat close to each other? So we want to take more readings, and graph the relationship. I think. Yes. Basically, it says plot a graph. Another one that's pretty much universal in every experiment, for timing at least, is that hard to measure time accurately due to human error, or human reaction time, basically. And to do this is that record a video with timer in hand, or as they say, in view. And essentially what this means is that you can actually like go frame by frame and just record when it actually hits. Another idea is to use like a high-speed camera, but that's depending on the actual thing. You can also use sensors. It's pretty much the same thing. And honestly, the other 4 points in this question are depending on the experiment itself. So for example, in this case here, to make it more accurate, we can probably increase the length of the tube. It can actually be hard to measure D here because if we're using a meter stick, how do we know it's actually straight, right? So the best way to do this is actually using a screw gauge, which actually can measure much more precisely and thus make the results more accurate. So this reduces a source of systematic error, I'm pretty sure. And yeah, it also includes that some of the balls are difficult to use. You can just use more balls, I guess. But this is simply just for this experiment alone. Let's take a look at the 3, 2, 1. Maybe it's an interesting experiment. We will investigate the elastic properties of a rubber cord. Oh, materials. Okay. Yeah. All right. So it's pretty much the same thing here. It's like the two trials, and you want to graph more, as well as in this case, it's probably this L. So this length might not necessarily be measured correctly. Right? Due to something called parallax error. So this is a pretty common error. So when you're measuring something on a ring stand, this is also another thing you could talk about is parallax error. Moreover, for like oscillation type problems, oscillations might be difficult to record. So then what we can do is that we use a more accurate like measuring thing. In the mark scheme, it says to use a traveling microscope. Sure. Yeah, whatever. I have no idea what that is, to be honest. And then there's also like time stuff. You can also do that as well. But essentially, it's like go out with it, honestly. Just to make the most plausible answer. Another thing for answering this last part is that this 1 corresponds to 1. So you don't want to write, oh, not enough trials. Oh, God. Not enough trials. Oh, no. And then you're going to say here, use a video with timer in view. Obviously, these two do not correlate at all. And if you do this, you're going to lose marks for sure. But yeah, that's generally this paper, I guess. Yeah, I don't know. I'm not too sure about data recording, to be honest. The thing is, like, you want to take the stuff that you know, and then an extra 1 sig figs as an estimated digit. I've learned it to do 0 or 5, but honestly, I don't think it matters too much. But yeah, the graphing is a pain, but it is essential to learn how to graph it properly. And in the future, you can actually use software to graph it, and it's way more better, honestly. In my stats class, when we're doing like linear regressions for a table, oh, that stuff was genuinely so clean because you can just see the line just go through the points and it looks so even. And then like looking at the residual graph, god damn. But yeah, I digress. It's pretty cool stuff, honestly. Might be a nerd for this, honestly. It is what it is. It's pretty fun stuff. They give you approximately 180. This is also another possible source of error because it's hard to measure angles of the protractor without an actual device. Another thing that you should keep in mind is that this experiment, the second part, is designed purposely to be a terrible experiment simply because they want you to critically think about possible improvements to achieve more accurate and precise data. So yeah, have a good night, guys, or good morning, guys. So yeah.